So overall, you guys did pretty good. The average was 78. The exam range was 50 to 100. So that's kind of a perfect distribution, right? Had a really nice distribution of grades. Average kind of right in the middle, even a little high. And we're going to go over the problems and kind of some like common mistakes and things that I think are gaps in your all's understanding, or I've seen are gaps in your understanding based on the exam results. So we'll just start kind of right at the beginning and go through the problems, and then please let me know if there's specific things that you were confused on or things you want to talk more about. Yeah, homework 5, we can grab that at the end of class. So the first problem, I'll just go through the solution. I posted it yesterday, and then we can kind of write down common mistakes. First problem, just what do you need for heat transfer to occur? Temperature difference has to exist. If you don't have a temperature difference, you won't have heat transfer. And then we talked about, the next question was just kind of describing convection. And we've talked about this several times in lecture. So it's heat transfer between a surface and a moving fluid. It consists of two mechanisms, diffusion and advection. Diffusion is the heat transfer that occurs based on the microscopic motion of molecules and atoms, and then advection is due to the bulk motion of the fluid. So that's really what I was looking for there, just kind of the description that we've gone over in lecture. So the third problem, we had air flowing over the outer surface of a circular tube. So this was basically a composite cylinder problem. It was worked very similarly to all the composite cylinder problems that we've done in homework or in class in recitation. So you had some information about the temperature of the fluid at the inside of the cylinder and the outside of the cylinder, and then dimensions. The only kind of part of this that was slightly different from just like a standard composite cylinder was, instead of giving you the full heat transfer coefficient just as a value on the outside, you had to just integrate this expression for the local heat transfer coefficient. So just combining what we've done with composite cylinders with integrating over the length to determine the total heat transfer coefficient. So this one, just wanted you to draw out the thermal circuit and just kind of write out the resistances based on the values of the dimensions, the length. For the second part, that was just putting that in the kind of thermal circuit format. So just writing the equation based on the thermal circuit and solving for Q. And this was the part where you had to realize, okay, this H sub naught, we're looking for Q over the entire tube. So the H sub naught needs to be integrated from a local expression to get the full expression over the entire tube. So that was just integrating from 0 to the length of the expression for the local coefficient, and then you get that the average or total H is 28. Plug that in and you can get the solution. The next part, I just wanted you to write down kind of the 4 standard assumptions that we always make when we use the thermal circuit setup. And these are the same assumptions that are written on the equation sheet and that we talk about when we derived the thermal circuit problem. So remember, you have to have a steady state, one-dimensional heat transfer, no energy generation, and isotropic materials. And then on the last part, just not solving for radiation or anything, but just saying, okay, now we have radiation on the outer surface, and that's just going to mean that it's convection and radiation in parallel. So just changing this last part of the thermal circuit. So overall, you all did pretty well on that one. Were there any specific questions? Anything that kind of specifically tripped you up on that problem? Nothing in particular? So kind of the most common mistakes we found when we were grading was just a lot of people use the diameter instead of the radius. That's just kind of looking at the problem, you know, knowing that the diameter is given, using the correct one for calculating area. And then not realizing that you could just integrate h over the length of the tube to get the total h. And some of you just kind of left it in that expression. So we gave you the points for, kind of showing that you could bring it through, but not for integrating and actually calculating the value. Okay. There's nothing specific on that. Let's talk about the next one. So this was a first law problem. So basically for this one, I wanted you to, so first of all, just realize that radiation is the only mode of heat transfer that can occur in a vacuum. So you have to have a medium for conduction and convection to occur. So we're assuming this is in a vacuum, and you're talking about the heat transfer between the pod and space. So that can only be radiation. And then put a control volume around the pod and apply a first law energy balance. So I told you to start with the most general form of the first law on a rate basis. So basically the form that takes the internal energy and breaks it down into its components, and then cancel terms as appropriate. So that was this form. So kind of the, I think, most common mistake on this one, and where there's a little bit of a gap in understanding, was kind of realizing the distinction between stored energy and energy transfer. So the left-hand side of the equation is energy that is stored in the control volume, internal to the control volume. And that can be many different types of energy: mechanical, potential, internal. For heat transfer, we consider mechanical, so kinetic, potential energy, and then thermal, sensible and latent. And then that's equal to the rate of change of stored energy, which is made of these components of types of energy, is equal to the energy that is moving in or out of the control volume plus the energy that's generated internal to the control volume. So you can think about this left-hand side, the stored energy, the rate of change of it, can be changed by, if its components change with time, or if there's energy in or out or energy generated. So with that, we can kind of look at the problem setup and figure out what we can cancel. So we're taking the stored energy broken down into its components and saying that's equal to the energy in, out, and generated. There's no gravity, so there'll be no change in potential energy. We're assuming there's no phase changes occurring. And then the temperature of the pod is going to be greater than the temperature of space. So there's going to be only energy out. There's going to be no net energy into the pod. Any questions on that so far? Anything that's confusing? Okay. And then you kind of break this down as we've done before. The energy out is only going to be heat transfer. You can express energy generation as Q dot times V. We didn't require you to do that. And then just recognizing that the kinetic energy and the internal energy, the thermal energy of the pod, are both changing with time. So we said that it's a time-dependent velocity, and the internal energy, or the temperature inside the pod, is slowly increasing. So both of those things should tell you this is not a steady-state problem. If the velocity is changing with time and also the temperature inside the pod is increasing with time, then it's not a steady-state problem. So you can express those changes of the kinetic energy just using the kinetic energy equation, 1/2 mv squared, taking the derivative of it, rate of change of kinetic energy, and then the rate of change of the sensible energy. So this equation that we have, the rho vc delta t on a rate basis, dt with respect to time. And then you know that Q out is only radiation, so you can express that as the radiation equation. And we didn't require you to write everything out fully exactly in this form. We gave quite a bit of partial credit, you know, if you just kind of recognize the things that you needed to cancel out and had those still in the final form. Okay, questions on this? I think there's still a little bit of kind of a fundamental misunderstanding about stored energy, especially thermal energy, and Q, heat transfer. So thermal energy is the energy that's inside of a control volume or internal to a control volume. So stored energy, kinetic, potential, internal. And then thermal energy is how much of the internal energy is due to sensible or latent components. So that's the motion of the molecules or energy due to phase changes. And then heat transfer is that energy in motion. So it's thermal energy that's moving from one kind of location in a material to another location, or from one medium to another medium due to a temperature difference. Questions on that? Okay, so thermal energy, every object with a finite temperature has some thermal energy internal to it, and then that thermal energy is transferred to another object or medium if there's a temperature difference. And that's Q. Versus big U is the thermal energy. Okay. No specific questions? All right. The next problem was a lumped capacitance. So you have a rod at a uniform temperature, suddenly exposed to a cooling process. So that should tell you immediately, okay, sudden change to the boundary conditions, transient cooling, lumped capacitance. That's the only way we've talked about handling transient problems. And this one was very standard lumped capacitance calculation. Calculate the BO number, make sure it's valid to use lumped capacitance. And if you calculate it correctly, it's much smaller than 0.1. This was a very common problem, not having the equations for the volume or surface area of a cylinder right. Probably the most common mistake on the exam. So volume is the cross-sectional area times the length, pi r squared times L. And then surface area, the perimeter, so the circumference times the length, pi d times the length. There was a little bit of a misunderstanding on whether or not you needed to include the ends of the cylinder. And if you did or if you didn't, we gave you full credit regardless. We didn't take off for that. But the reason that you don't need to include the ends of the cylinder in this problem is because it is a very long, thin rod, right? 1 meter long, 40 millimeters in diameter. And the kind of outer surface is exposed to this cooling process. And so the heat transfer is going to be almost entirely in the radial direction. And when you're talking about the surface area that matters is the relevant surface area for heat transfer. So in that case, it's just the radial surface area. You're not going to have heat transfer in the axial direction, or it's going to be very, very negligible. So you don't have to include the surface area of the end plates. If you did, it makes basically no difference in the calculation because they're so small, which is why we neglect it in the first place. So you got basically the same answer. And then kind of the basic or most fundamental assumption of the lumped capacitance method is that we're saying spatial temperature gradients are negligible, right? So the temperature of the rod is uniform throughout the entire thing. So then the surface of the rod and the center of the rod would have the same temperature. And so there were some mistakes on kind of using the lumped capacitance method for part A and then calculating part B using some other method. So if you're assuming that the lumped capacitance method is valid and that's what you're using to calculate part A, then you should be able to conclude that, okay, the temperature in the entire rod is going to be uniform, so it's the same temperature for the surface and the center. Okay, questions? This one was, everyone did pretty well on this one as well, yeah.
Just since you had the two kind of separate questions of that, I interpreted that as kind of you wanting us to use the separate methods and kind of seeing how close they would come. And then I got documents doing it that way.
So we haven't, there's not really another method for calculating transient heat transfer. There were a couple of you who, and we'll talk about this on the last problem as well, because this was a similar misconception. There were a couple of you who kind of tried to calculate the total heat lost at like big Q in energy, and then divide that by the number of seconds to get a heat rate, little q, which you can't do because the rate of heat loss is not linear. So if you take the total heat rate, the total amount of joules lost over 35 seconds, and you just divide by the 35 seconds to get the rate, that's just kind of the average rate, which is not the same as the instantaneous rate of cooling. So for lump capacitance, we talked about it's kind of like an exponential cooling rate. So you have to use the lump capacitance method. You can't just calculate the total Q and then divide by the time, because that heat transfer rate is not the same as if you calculate using the lump capacitance method and assume that it's an exponential decay in cooling. Does that make sense?
I mean, that's not the method I use, but that makes sense.
Okay, well, yeah, we can talk about yours later then. Yeah. But yeah, this is, the lump capacitance is the only way we've talked about transient problems, so that's how you should approach it. Okay, any more questions on that? All right. So the last problem. So this problem is basically you have a wall with energy generation, it's insulated on one side, and there's a room that's being heated by some fins. And this problem is significantly simplified if you kind of step back and look at it from a first law perspective. So really no matter where you apply the control volume, you should get the same answer. So let's say you apply the control volume around the entire room. And we know that, let's just write it here so we can look at the terms that will cancel out. So if you apply it around the entire room, you know that heat is leaving from all walls of the room aside from this left-hand wall. So there's going to be some energy out. We also know that the temperatures are all constant in time, so it's steady state. And heat is leaving through these walls, and this side of the wall is insulated, so there's going to be no energy in. So you're left with energy out equals energy generated. So the total energy out is 2004 watts, and that's all got to come from this Q dot. So Q dot is watts per meter cubed. So if you just multiply that by the volume of the wall, that gives you watts. And you know the volume of the wall because you know that it's 0.5 thick, 4 wide, and 3 tall. So you can just calculate what this Q dot is from the fact that this is Q out, and you know the volume. If you apply separate control volumes, the same thing is true. So you could apply the control volume just to the inside of the room here, and then that would show you that, okay, now it's steady state and there's no energy generation. So there's some energy out and there's some energy in. So the energy in through this wall must be 2004 watts to equal the energy out. And then you can apply another control volume just around the fins and say, okay, there's 2004 watts out from the fins, so there must be 2004 in, because again, steady state, no energy generation. And then if you apply it to kind of the inside of the wall, this side is insulated, so there's no energy in, it's steady state, so you get that energy out equals energy generated. And again, you can show that the energy generation times the volume is going to equal the energy out. So however you apply the control volumes, you get the same result. And if you calculate the Q dot as Q over V, then this problem, the first part of the problem to calculate the temperature at the base of the fins, just becomes a heat diffusion equation. So heat diffusion in a plane wall We know everything we need to know to calculate the temperature distribution. This is identical to one of the problems that we did on the homework. So you know, starting with the general form of the heat diffusion equation, you can assume that heat transfer is one-dimensional, isotropic materials, steady state. So then it reduces to this form of the heat diffusion equation, which you just integrate twice and apply the boundary conditions, insulated and constant temperature on the left-hand side to get the temperature distribution. And then once you do that, you can just plug in 0.5 to know the temperature at the base of the fins. So this was kind of like very similar problems to what we had on homework, just two of them together. So over here, temperature distribution, heat diffusion equation. And then once you know the temperature at the base of the fins, what you know is Q total, right? Because it's the Q from the entire wall. So I specifically wrote it like this so you didn't have to use those equations for the fins with Koch and Cinch and Tanch. So you could just take the Q from the fins and use the equation for the total heat transfer rate. So this equation is the total heat transfer rate, so the heat transfer from the fins and from the base. And then you can solve for the efficiency of a single fin based on that. And then all you need to know after that is the number of fins, the fin surface area, and the base surface area, which are all calculated in a way very similar as we did on some of the fin array homework problems. And then you can just rearrange and solve for the fin efficiency. So first I'll ask you guys, so let me know if you have any specific questions about this, and then I'll talk about kind of what the most common mistakes on this one were. So is there anything that's specifically confusing? Yeah.
So I tried to get the efficiency by doing overall efficiency, and then there was an equation that we were given in classes, like overall efficiency is equal to
The eta sub naught.
Yeah. And I definitely did not get the right answer with that, and I'm like wondering, like, maybe I just wrote the equation down wrong or something, but like shouldn't it come up with the same answer as the other method if you do like the overall efficiency?
It should, yeah, it should.
Okay.
If you use the right rates or the right values for the heat transfer. Yeah. But that's kind of another common mistake that I'll address, was using the wrong Q in the equation. Yeah.
What is the problem indicated that the convection coefficient was the same for the fins and the wall?
So, yeah, so we've always assumed that. Basically, when we introduced fins, we said, okay, we have a flat wall and the fins, we're just going to, if we have one H value for the fins, we're just going to assume that it's the same for the wall. And it's, probably an approximation, but is a good enough approximation that we're going to use it. Yeah. And yeah, that's something that I would be happy to clarify during the exam. Yeah. Anything else? Okay, so I realized that this was a tough exam, and I think you guys did pretty well. I'm really happy with how you did. I mean, there was a 78 average, and it kind of highlighted just a couple of points that really you have misunderstandings on, but everything else I think you did pretty well on. The exam was too long. I fully recognize that. So I basically can gauge the exam length on how long it takes me to take it and how long it takes the TAs to take it. But the good news is, and based on that, it seemed very reasonable. The good news is I now have a data point, right? And I can recalibrate for the final. Okay, so I now know what multiplication factor, if it takes me this long, what to multiply by for it to be reasonable for you guys, okay? So I did not intend for it to take you the entire 2 hours for all of you. And I feel like that was the point that really kind of freaked you guys out a little bit. That was like a little bit traumatizing. You're like, this is so much. So you did fine, okay? 78 average, it's 20% of the grade, all right? Homework and labs are still way more than that. And overall you did well. So I'm pretty happy with how it went. Okay? Anything else? Anything you really want to complain about? All right. So let's talk about the most common mistakes on this problem, because that really highlighted kind of a couple of things that there's really a gap in understanding. So the biggest thing, the most common mistake I saw was where you all tried to calculate the T on this side of the wall using the conduction rate equation. So you basically said, okay, Q is negative KA delta T over delta X. I know Q, you calculated, you applied the control volume, you figured out that this was 2004 watts. You know the K, that's given. You know the area. So this delta X, that's the length, and then you know one of the sides of the wall. So you're like, okay, all that's left is this other temperature. Let's plug this in and figure out what the answer is. And it really seemed like a lot of you kind of knew that was wrong, but you weren't really sure why, or you didn't really know what else to do. So the reason that that's wrong is because this is only equal to negative Ka dt dx if the temperature distribution is linear. So I'll draw it out. So if we have X and T, temperature changing as a function of X, if, so 32, and it ended up being like 29 or something. So if the temperature distribution is linear, looks like that, versus in a wall with energy generation, it looks something like that. So you can get away with using this equation for a linear temperature distribution because the slope over the entire length is going to be equal to the slope instantaneously. Does that make sense? So it's linear, so you can say that. But if it's not linear, which is the case with energy generation, and most of you kind of picked up on the fact that, oh, there's energy generation, I don't think I can use this equation, but I don't know what else to do, which we gave you partial credit for doing that. If it's not linear, then you're basically saying Q is equal to this right here, the total delta T over the total delta X, instead of equal to whatever the dt dx at kind of the specific location that you're considering is. Does that make sense? And that's also kind of what I was talking about if you work the transient problem as just calculating the total energy joules out and then divided by the time. You're just assuming that it's kind of a linear rate of change of temperature with time. But in reality, it's more exponential. Okay, so that was kind of the biggest gap in understanding there. So quite a few of you did it that way. Quite a few of you did use the heat distribution equation, get the right, or close to the right temperature. And then for part B, this was using the total Q. So you know that the total Q out is through the wall, and you can use this equation. Quite a few of you used or tried to use the fin efficiency for a single fin. So it does, the problem asks for the efficiency for a single fin, but what you know is the heat rate, the total heat rate for the wall. And a lot of you actually did that successfully. You realized, okay, if I'm going to use the efficiency equation for a single fin, then I need to calculate what the heat transfer rate just from the base is and subtract that from the total heat transfer rate for the entire array and then divide by the number of fins. And then that does give you the correct number for just the heat transfer rate from one fin. And quite a few of you did it that way and did it correctly. So that's basically just the same thing as this equation. So you just took the total Q, you subtracted the Q from the base, you divided by the number of fins, and then you had Q out from one fin, and you could just solve this for the efficiency of one fin. Where this did not work was if you just took the total Q and divided by the number of fins, which was another common mistake. So you're kind of neglecting the fact that there's heat transfer from the base as well. Or yeah, if you use some kind of other efficiency equation where it should have worked out, but you didn't quite calculate the Q correctly, accounting for the fact that it's from all of the fins and from the base. Okay, so any last questions on that? Nope. Okay. All right, so we've got about 20 minutes left. I want to go through and finish up some of the material on internal flow. I'm going to post homework 6 today. And because we did not have a recitation, so you didn't get to see example problems for internal flow, I posted some recitation problems on Canvas with just the problems and then the solution fully written out with all the explanations, so you can refer to those. And feel free to come to office hours or email me to set up a time to talk about them if you don't understand them. And then on Friday, I want to do kind of a little summary wrap-up of just how to approach convection problems, because we've kind of gone through, introduction to convection, and then we talked about external flow and internal flow, and we didn't have a recitation for internal flow, and we skipped a homework week. So we've been a little bit out of practice, haven't had as much time to kind of practice convection equations as I would like. So I want to just go through kind of a step-by-step summary of this is everything we know about convection, and this is kind of how you can approach solving problems. So we'll do that on Friday. But I want to try and finish up the notes for just the laminar and turbulent flow and circular tubes for internal flow. So let's go back and remember what we were last talking about. So we were talking about internal flow and the development of the velocity and thermal boundary layers. And we said that the thermal boundary layer continues to, or the temperature profile continues to develop even after the flow becomes fully developed. And so because the temperature profile continues to develop, we have to define some mean temperature, so the kind of average temperature across a cross-section that we can use for our calculations. And doing that, we can kind of set up a first law balance around a differential element in a pipe, and then solve it for a differential equation. And then we can apply boundary conditions, either a constant surface temperature or a constant surface heat flux, and then we can get the temperature distribution in the pipe for those boundary conditions. So we talked about what the temperature distribution is for the temperature distribution of the mean temperature, so how the mean temperature changes with x, for a constant surface heat flux and a constant surface temperature, this one. So that's kind of where we ended. And we said that the convection heat rate across the entire, considering kind of a full tube or a section of a tube, is going to have to use this log mean temperature difference because the temperature changes exponentially as you go down, as you increase in X position. So the mean temperature changes exponentially. So you can't just use the direct average of the temperature at the beginning and end. You have to use this log mean temperature difference to account for the fact that it's changing exponentially. Okay, so that's where we stopped with internal flow. Questions on that from Monday? Okay, so we'll talk about now laminar flow in circular tubes. And so we talked about how there was two regions in internal flow. There's an entry region where the flow is still developing, and then there's the fully developed region. And this is true for both the velocity and thermal profiles or boundary layers. So right now we're just going to talk about laminar flow in the fully developed region. So we're going to consider an incompressible constant property fluid. And again, fully developed flow, laminar flow in a circular tube. For this problem, the temperature distribution can be solved analytically. And so rather than the empirical method of determining the Nusselt number, where you do a bunch of experiments and kind of collapse all the data and come up with an expression for the Nusselt number, and from there you calculate H, the temperature distribution can be solved analytically, so you can directly calculate the temperature distribution, the derivative of the temperature distribution, H, and then calculate the Nusselt number from that. So that's kind of how this solution was derived. So from the temperature distribution, you can solve for H and then the Nusselt number. So we've got our two different boundary conditions, a constant surface heat flux, the Nusselt number, which remember the diameter-based Nusselt number is HD over K, is equal to 4.36. So it's a constant, and that kind of makes sense because we said in the fully developed region H is a constant, and the diameter and K will be constants. We're treating them as constant. So the Nusselt number is just 4.36. And then for a constant surface temperature, the Nusselt number is 3.66. So again, constant, but just for the different boundary condition. And then again, when you're evaluating the Nusselt number, usually you're trying to find h. So you can find an expression for the Nusselt number, and then you're trying to find h, so you have to evaluate the Reynolds number, Prandtl number for external flow, or other conditions where it depends on the Reynolds and Prandtl number, and also k. And so typically, for external flow, we evaluate the fluid properties at the film temperature, right? So the mean between the surface and the ambient temperatures. But for internal flow, the temperature of the fluid, we're going to assume is given by the mean temperature at a cross section. So for internal flow, K, the thermal conductivity of the fluid, is evaluated at the mean temperature. Okay, questions on that? All right, let's talk about now the entry region. So there's two kind of, yeah.
So my question was, T sub m changes with cross sections, right? So is K evaluated at like T sub m bar?
Yeah, great question. So yes and no. So if you are evaluating the local H, then it's just T sub m at that cross section. If you're evaluating the average H, then it's the average T sub m between kind of the inlet and the outlet. So it's evaluated, we can write down, it's evaluated at T sub m for local, Nusselt number, and H, and it's evaluated at T sub m bar, which is the average of the mean temperatures at the inlet and outlet that you're considering for the average Nusselt number and therefore average convection coefficient. For the entry region, there's two kind of separate problems that you have to consider. There's the thermal entry length and then the combined entry length. So the thermal entry length is a little simpler, and it assumes that the thermal boundary layer develops in the presence of a fully developed velocity boundary layer. So this could occur if kind of two different situations. So if the pipe had an unheated starting length, so if basically the temperature of the fluid and the temperature of the pipe were the same temperature for kind of a portion of the pipe initially, then the velocity boundary layer would start to develop, but there would be no thermal boundary layer until you got to a part in the pipe where it was heated. So basically, by the time you got to the part in the pipe where it was heated, the velocity boundary layer would be fully developed, and then the thermal boundary layer would start developing at that location. in the presence of a fully developed boundary layer. So that could occur if the pipe has an unheated starting length, or for large Prandtl number fluids. So for those, the velocity boundary layer, the momentum diffusion is much higher than the energy diffusion. So the velocity boundary layer develops much, much more quickly than the thermal boundary layer. So you can essentially assume that the velocity boundary layer becomes fully developed so quickly that the thermal boundary layer is then still developing in the presence of this fully developed velocity boundary layer. So large Prandtl number fluids such as oils. So for the thermal entry length problem, for a constant surface temperature, the average Nusselt number is 3.66 plus 0.0668 times this Gratz number over 1 plus 0.04 times the Gratz number to the 2/3. And that's defined as d over x times the Reynolds number times the Prandtl number. So again, that's laminar flow in a circular tube, talking about the entry region where the velocity boundary layer is fully developed, but the thermal boundary layer is still developing. And you have a constant surface temperature boundary condition. So lots of restrictions on this equation. For the combined entry length problem, this should be a dash. Keep our notation consistent here. So we've got the thermal entry length problem where the just the thermal boundary layer is developing, and then the combined entry length problem where both boundary layers are developing at once. And then for the combined entry length problem, again, constant surface temperature. Okay, this one is pretty long, so we'll wait until Friday to write it down. But remember, this one is for thermal entry length problem and then for combined entry length problem. Okay, and I'll see you all on Friday.